In the last video, we discussed this adjunction between the functors lambda and gamma. And as I mentioned in the first video, this adjunction will actually restrict to an equivalence of categories. It will restrict to an equivalence of categories when we look at the right subcategories. So what are the right subcategories? Well, actually I guess there's more than one answer because you can pull more than one equivalence out of this guy. But the one that we're looking at now is with the following subcategories. So the subcategory of the category of presheaves on X, that's going to be something familiar. That's going to be the category of sheaves on X. That's a subcategory over here. And on the spaces side, this will be the subcategory of Etale spaces over X. That'll be a subcategory of the category of spaces. And the functors gamma and lambda will play nicely with these subcategories in the sense that if I apply gamma to an Etale space, I'll get a sheaf rather than just a presheaf. And if I apply lambda to a sheaf, I'll get an Etale space rather than just getting a space. In fact, more is true, and we'll see later. But what was just an adjunction upstairs will become an equivalence downstairs. That's what I mean about getting an equivalence when restricting on the right subcategories. So we just had an adjunction between lambda and gamma up here, but it'll become an equivalence on these subcategories. So this is kind of the next big thing that we want to see in this mini-series. And the first step is finding out what this means, what Etale means in this context. So that's the purpose of this video, to define Etale morphisms, and thus to define the category of Etale spaces over X. So let's do that. So let's let the map P from E into X just be some continuous map. And we'll say, or we're going to say, that P is Etale if the following two conditions are met. First of all, well, yeah, let's say this: if for every if for every E inside of E, for every point little e inside of big E, there exists an open neighborhood, an open set U of E containing E, such that the following two things are true. So such that first, P of U of E is open. So it's an open subset of X. And two, the restricted map, I guess I'll draw this as U of E, P restricted to U of E onto P of U of E, is a homeomorphism. So that's it. These two things together make the Etale condition. This is sometimes phrased a little bit more snappily by saying just that P is locally a homeomorphism. And this is the way that I like to think of the Etale condition. Who knows what P is doing in general, but we can sort of take comfort in the fact that for every point inside of this set E, for every point inside of the space E, if we look close enough at that point, if we sort of restrict ourselves to a sufficiently small neighborhood about that point, we know that P is a homeomorphism. Who knows what it does in general, but at least locally it's very nice. Okay. So I want to point out immediately kind of how this is different from a covering space. So the definition of a covering space is kind of similar, I think. And I think a good way of understanding what Etale means is to sort of understand why it's different from the notion of a covering map or a covering space. So it's always going to be true that a covering map is an Etale map. That's always true. But the reverse implication does not hold. So Etale does not imply covering. And the reason for this basically is that in the covering situation there's some sort of uniformity of open sets on the fiber. I mean, right? What is the covering definition? For every point in the base space, you pick an open neighborhood and you pull it up to a collection of homeomorphic spaces in the fiber. So you've got a whole collection of similar looking open sets over your base set. And in the Etale situation, you don't have that uniformity. In other words, these open sets sitting on your fiber may be different looking. So, as I said, I think this is a good way of understanding what Etale means in practice. So let me make this into an example. Rather, let's make it into a pseudo-example, since I'm going to be drawing pictures, rather than looking at a specific actual case. So we want to see what the difference is between Etale and covering. Let's let this be the covering world, the covering space world, and this will be Etale spaces over here. And let's do this over R2. So our base space X will be equal to R2. We'll draw it in both worlds here. And then we'll have our overspace sitting up here, E. So what happens in the covering space situation is that while you look at some point in the base space and you pull it up to its fiber, let's draw 3 points for the fiber, and there is some neighborhood down here such that when you pull up that neighborhood you get a bunch of exact copies of it. So the way that I draw this won't be perfect and it won't look like exact copies, but that's how you should imagine. All of these things are the same. This one really doesn't look the same, but it's meant to be. So you pull this up and kind of these open sets sitting on the fiber all look the same. They're all homeomorphic to each other, very uniform. That's what's going on in the covering space situation. And what's going on in the Etale space situation is similar, but there's sort of more variation allowed. So again, let's imagine that we have a point in the base space and we pull it up to the fiber. And it will be true that if you pick one of these points in the fiber, it's going to contain some open set, or it's going to be contained in some open set which is homeomorphic to its image. But different points in the fiber may have very different looking open sets in this regard. So maybe this one has an open set looking like this, and this one has something weird looking like this. And this set, this guy, it'll get carried down homeomorphically onto its image, and this guy will get carried down homeomorphically onto its image. But those two things may not be homeomorphic anymore. They may not be the same space. Maybe this guy looks something like this. So that's how I like to think of the difference between the Etale situation and the covering space situation. In the Etale space situation, these open sets sitting on the fiber may look very different, whereas in the covering space situation they all have to look the same. So there's actually a nice description of this that I like. This is from the book Sheaves in Geometry and Logic by McLean and Mordyke. And this is how they describe the situation. So this is, again, in their example, this is over R2. R2 is the base space. And if people have a copy of this book, at least in my edition, this is on page 88. Anyway, here's the description. It says, "Thus, the vicinity of the fiber over each x and x can be pictured as a serving of shish kebab. Through each point of the fiber there is a horizontal open disk on which the projection P is a homeomorphism to a disk in R2. The disks at different points of the fiber, pieces of lamb or onion, say, may come in very different sizes." So that's the point. This is supposed to be some sort of shish kebab over here. Alright, so that's the distinction between a covering space and an Etale space. Now let me just spell out something. I've been kind of interchanging Etale space and Etale morphism here, so let me just formally tell you what an Etale space is. So this is another definition, I guess. A space E over X is called Etale if the structure morphism P is an Etale morphism. So people say Etale space, but really this is a property of the structure morphism. It's the structure morphism which is Etale. Okay. So given that, we now actually know what an Etale space is. And now we know what the category of Etale spaces over X is. It's just the category whose objects consist of Etale spaces. Etale spaces. So that just means P is Etale. And this is a subcategory of the category of spaces. And we'll see in the next video we'll see soon how this adjunction upstairs becomes an equivalence downstairs.